Okay, delighted to be here. My student and myself will be presenting whole body controllers for dynamic locomotion, and really our ultimate goal is to move as quickly as possible into rough environments, and this kind of picture illustrates the connection to humanoids, in this case, point-foot humanoids. Whole body control has been around for about 15 years, at least from my point of view, in the sense of controlling center of mass behaviors under contact constraints. Again, from my point of view, the beauty of whole body controls is its versatility to create new tasks and portability to adapt to new, different control structures, to different road structures. Point-foot robots are interesting as an academic platform because they have very fast dynamics and hard impacts. For instance, our biped Hume generates 2.5 steps per second and undergoes 100 milliseconds double support phases. And that poses challenging problems for whole body control, and that's what we want to explore. We want to entertain ourselves in exploring these difficult transitions. Therefore, the lessons learned in point-foot robots can hopefully help to boost agility on humanoid robots with flat terrain in turn. We work with device whole body operational space controllers for point-foot robots, which cannot directly control the center of mass. We propose feedback control of internal forces to deal with the tuned torque controllers. We devise sensor fusion for post-estimation, and we devise dynamic locomotion planners and controllers to achieve unsupported balance. WBOSC is an inverse dynamics problem for a task level. It formulates second-order floating-based dynamics, many of you know. So the torque command corresponds to actuators only. We formulate task kinematics in actuator space. It is straightforward to formulate an OSC controller with a support consistent Jacobian. In multi-contact, there is a null space to the joint accelerations, which are those torques that do not produce any motion on the robot, and therefore correspond to the internal forces. What is interesting about this breakup is that both task motion and internal forces are fully controllable spaces. Therefore, we can create feedback controllers regardless on control level to control set point. Internal forces have a simple mapping shown here with respect to contact forces, and therefore we can use any optimization method to compute contact forces first and then transform them into internal forces. For this work, we wanted to demonstrate that whole body operational space control can handle the fast dynamics of point-foot robots, and then we can deal with CL-type actuators. Point-foot bipeds are different than humanoids with flat feet and from quadrupeds because they don't have any supporting polygon. So the pros and cons of WBOSC are shown here. We can accomplish accurate control, contact force control, regardless of the joint torque controllers. Priorities allows behaviors to automatically repress conflicting tasks. It has dynamic correctness. It supports execution of overdetermined tasks, exposes task-effective inertia, which is important for analyzing mechanical performance. And some of the cons are it hesitates to convert desired contact forces to internal forces, which is a hassle, and it lacks inequality constraints. Compared to other point-foot bipeds, Atreus walks continuously without relying on whole body controllers. It does not control your movement, relying instead on small passive feet. It hasn't shown the control of contact forces, for instance, to balance on disjointed terrains. Marlowe achieves 20 steps of unsupported walking. Hume, our biped, achieves 18 steps of unsupported balance, pretty close. Hume is not perfect. It suffers from high stiction and very flexible structure. It extends, it generates a curvature that yields 5 cm kinematic errors. Microstrain IMU is very noisy and has large bias error. The motion capture system that we use has occlusions and latencies, and we sought to run WBOSC at 0.66 milliseconds to raise impedance gains. And I'm going to switch to now the person that has done the real hard work, which is my student, Don Kim, so please come over.
Thank you. Let me explain how we modify and implement a whole body operational space control in our point-foot biped. This is a diagram of our end-to-end control scheme. I'm going to start explaining the test controller. The input of the operational space test controller is left-hand trajectory. In the single support space, we control the foot position and central mass height, roll, and pitch. The foot trajectory is obtained using fourth-order polynomials. The desired end position, which is the landing location in this case, is computed by our locomotion planner. In double support phase, we control the orientation of the body and the center of mass height. We also control the yaw orientation in double support phase to stabilize the motion. We also formulate the contact transition process. In this simulation, film is dynamically stepping, and the red lines show the reaction forces. To reduce the jerk due to the contact constraint change, we devise a transition technique. The idea is simple. We first compute the reaction forces in double support phase and choose the part of it that belongs to the leg about to be lifted. Then change the controller to single contact and add a transition force that corresponds to the previous lifting. As the foot starts to lift, we gradually reduce the transition force to 0. To show the effectiveness of the technique, we show the experimental result. The left figure corresponds to the D torque data as the robot performs one step. The white space between the discolored space corresponds to the transition between the single to dual and dual to single. As you can see, those transitions are very smooth. Let's talk about the internal force control. The resonance contact force can be calculated with various methods, such as multi-contact matrix or QP method. In our case, we compute the internal force by the simple geometry and force balance computation. Given the terrain at 45 degrees and 200 Newton weight, if the robot applied a 100 Newton tension force, then the reaction force will be normal to the surface. This is the experimental result. Hume controlled the position of the center of mass while keeping the 100 Newton tension force on the split terrain, and also show the different impedance behavior, compliant in the horizontal direction and stiff in the vertical direction. Let me introduce our sensing process. We use the IMU for pose estimation. However, using lens-based IMU, which has the limited performance in terms of the bias and noise level, is not enough to get the clean and accurate orientation. To work on this, we augment our sensing with a motion capture system. Let me explain how to get the orientation from the motion capture data. The translation and rotation of the robot's body make an alignment between the reference and measure the LED positions. And we reformulate the alignment to the linear matrix system. It also incorporates the terms representing the removal of the data due to the occlusions. By combining motion capture updates and IMU's updates into single matrix systems, we achieve the sensor fusion. Let's talk about the planner. Okay. So around the middle of the lifting motions, the center of mass state is delivered to the planner, and the planner predicts the future center of mass by integrating the dynamics of the prismatic inverted pendulum until the end of the swing time. From the switching state, the planner searches the next landing location, making the center of mass velocity becomes 0 after time t5. The planner can handle any type of the terrain thanks to the numerical integration. This dynamic simulation and Hume is this dynamic simulations, Hume is taking the steps over the 7 centimeter obstacle. This is the experimental result.
Just wait a little bit.
This is the experimental result. The simulation of the several experimental We are planning to redesign the part of the leg structure to be more rigid, and also switch to the high-performance IMU that has 2 orders of the magnitude lower bias error and noise density. Thanks for your attention.
Any questions? So maybe you can explain. So you have the point foot system. And as you can see, it has to always do the motion in order to keep balance. So what would happen if you would add a foot and you would have like continuous contact with the ground?
Well, I think at a certain point when you start really walking really quick, you want to actually rely on completely under-actuated dynamics, so complete dynamic walking. And we are hoping that the methods that we develop here, they can be, translated as well to flat foot. But basically, the main difference is we are not controlling the X and Y center of mass position. So that might be a route to go as well in humanoids with flat feet. They have to maneuver really quick and do rough terrains, just not attempt to control the horizontal direction of center of mass. Yeah.
Any other question, please?
Do you rely on having, because most methods for coin fit robots rely on having impacts for the stability. Isn't this also a problem to have your robot continuously stomping if you want to do manipulation at the same time, or don't you see this as a problem?
You're asking if, well, I think we are addressing right now mobility. We haven't addressed manipulation. Does that answer your question, kind of? We want to walk in multi-contact using any possible link. Impact, for sure, is going to affect your structure and your controllers. I don't think we're at the stage that we have experimented with or thought about how to remove the jerk on manipulation. But nonetheless, we do have Series Elastic Actuators, and Series Elastic Actuators, they do absorb quite a bit of the impact. So we did an impact analysis. Actually, for the planning, we don't use an impact model. And the reason is because we absorb a lot of it, and also because the effective mass of the end effectors is pretty lightweight. But certainly we'll note your advice and try to do manipulation at the same time.
Since we're behind the schedule, let's thank the speaker. So the next presenter is Vincent Samy, and he's from CNRS University of Montpellier, France. And the title of his talk is Pulse Control Using Posture Reshaping and Active Lines.
Thank you for the introduction. So hello everybody.